Okay, thanks for inviting me. I would like to start, and thanks for the introduction. I would like to start with a problem. I mean, obviously, global warming. And what you see here is that the continents are warming up faster than the oceans. And this has to do, of course, with the evaporation over the oceans, cooling the atmosphere there, and not so over the continents. So continents are warming up earlier, faster. And in Europe, for example, Germany, it's now up to 2 degrees. This has, of course, an impact on the water cycle. And this I would like to show you here. There's an intensification of the water cycle, and I will try to lead you through. What you see here are observations. This is not models or simulation. It is observation, Earth observation. And what you see is that globally, do you see my pointer? That globally evapotranspiration increased quite steeply, because 70% of the surface is water. And precipitation also increased, but not as fast. And of course, the difference is then the drying up of the continents. For example, discharges is runoff, water availability in surface waters, a decrease globally. These are all global means, and also groundwater. We have less groundwater stored in the continents and in the land surface. And of course, this has also a regional component. There are wind systems. We have heard about the Indian monsoon, for example. Here, the regional pictures, this is the US. And what you all know is that we have this drying up of the West, where we have the forest fires and all that. But looking at Europe, the change is even stronger. So it is not that it is drier in Europe, but the change shown is here, the change in water availability stored in groundwater. So Europe actually is hit harder by the change. And you may ask, where is the water? If there's an increase in evapotranspiration and not so much in precipitation, where's the water? And it is mostly in the atmosphere. So there's a specific humidity. This is the water in a cubic meter of atmosphere over land surface. And what you see in bluish colors, there's an increase in humidity, in specific humidity, the water which is in the atmosphere. However, when you are looking at the relative humidity, this is a function of temperature. The temperature has increased, as I told you before, global warming. And there you see that the relative humidity decreased, and especially over continents again. And looking now at regional scales, I take here the example of Germany. This is Elbe River Basin in 2018, and it was the same 2019. This year, the year before, we have a consecutive drought of 5 years almost now. This is what we call Faser Rhine, the Rhine River at Cologne. This is Schwarze Elster, smaller tributary of the Elbe Basin. These are some of the lakes we have in our area. Arable land in the east of Berlin. And we even have partly water problems. This does not say we do not have enough drinking water, but the infrastructure is not adapted to what happens in the moment. And looking at simply at the water balance of the landscapes in our area, this is Brandenburg, Berlin, for example, we have roughly a precipitation of 600 millimeters. This is 1 millimeter is 1 liter per square meter, and an evapotranspiration of roughly 480 millimeters. Yeah, so only the rest of it is discharge. This is the water availability we have then firstly in groundwater, later in the surface waters. Of course, we have a bit of storage. And what I want to point out here is that vegetation really is a key actor. Most of the precipitation is transpirated by the plants. Interception is what falls on the leaves and evaporates from there. And only the rest is evaporation from bare soil, streets, houses, and all that. Yeah, so vegetation is really the key actor. And when we have a look at the development of the water availability in our area, we see that in blue, dark blue is the precipitation, and that we did not have really a strong decrease in precipitation. We had some dry years lately, but not really a long-term decrease. But what we have is a steep increase and quite robust increase in transpiration, evapotranspiration. And only what is between these two lines is a corridor of where we can maneuver, where this is the water availability. This is the water which we have in the end in groundwater and in the surface waters. And of course, we would like to increase or to counteract. And and you may imagine that there are really conflicts nowadays over this precious resource of water. And as I said before, I think the key actor here is the vegetation. It's not only so because of the energy fluxes with latent heat. This is transpiration and the radiation reflection. This is the albedo. Vegetation provides also because of the carbon cycle. We want to store carbon, but also because of hydrology, of course. And when I say that vegetation is, I think, the key actor, we have to think about how, in the end, landscape should look like in order to adapt or counteract. The role of vegetation, I think this has also been shown yesterday, is also immense when looking at the cooling effect, for example, of forests. This is Brandenburg, this is Berlin, this is Brandenburg, and this is the land use, and this is a thermal image. And what you see is that, of course, the heat islands in the cities, but when you have a look at where we have the forests in Berlin, you see that immediately the cooling effect of the forest. What you also see is this is a huge area of arable land, Magdeburger Börde, where we hardly have any forests, much hotter than the surroundings. And this is publication I recently found. It's called the Predominant Regional Biophysical Cooling from Recent Land Cover Changes in Europe. Of course, over centuries, there has been a decrease of forests, mostly, not always, but it seems to be that over the last, say, 4 decades, there has an increase of forests. And this is so, and these are again observations, satellite data. There has been a decline in agricultural land, mostly occurred, and this mostly occurred in favor of forests. So in the end, we have a net gain of 7 mega hectare of forests. And what the colleagues here have done is somehow the same what also Mr. Gosch has done. They applied a regional climate model and had a look at how the landscape influences already now the climate we have. And this is in line with what we are talking about. It seems to be that only this relatively small amount of additional forest we have led to a cooling, counteracting the overall global warming or regional warming, I must say, by on average something like 0.3, 0.4 degrees over Europe, looking at the entire continent. And looking at the seasons, of course, the effect is not there in winter. In winter, plants do not evaporate normally, at least not in our regions. But it starts with the March, April, May, the spring, the cooling effect, into the summer, and phases out in the late summer and fall. So how can we adapt in the end in a sustainable way? Precipitation is difficult to influence regionally. We can influence it partly. However, the recycling mostly takes place on larger scales. And this here, I mean, this is again scientific results from a colleague where you see how much of the water evaporating from land, or how the share of evaporated land to the precipitation locally. And you see that it is mostly beyond the northern west wind zone, that it mostly happens somewhere in the east, in the far east, and that the share of this recycled water in precipitation is much less in Europe, for example. So what else can we do? We can, of course, also influence evapotranspiration, and discharge runoff. And here, I think really a key actor again is vegetation, and with that, forest. And I think you have also heard about this forest conversion from pine tree to deciduous broadleaf trees. And the idea is pine trees are green over winter and immediately start evapotranspiration or transpirating with warmer temperatures, and broadleaf trees not so. And therefore you will have, and these are simulation results we have done for the entire region to see the effect on top without climate change, below with climate change. And the upper band is always broadleaf. This is beech, buche, and pine. Below kiefer. And what you see is a groundwater recharge, and that groundwater recharge, especially in spring, is much higher under beech, and the same with oak and Douglas fir, Douglasia. Yeah, and even under climate change conditions, there is a gain by converting the area from pine forest to mixed forest, for example. And because it is such a share also of the landscape, I think that this will really have an effect on a river basin scale. It has, of course, also to do with the age of the trees, and younger trees. Under younger trees, we have much more groundwater recharge, and here again, for a pine tree and for beech. But in all age classes, the groundwater recharge is much higher under mixed forest or deciduous forest. And these are really measurements. Okay, there's a lot of pressure, of course, on forests now, and it is not only forest fire, and we have many trees dying because of the droughts and beetles and all that. What else may help in the end to harvest water? And another actor and another measure discussed widely is water retention, and I'm very much in favor of water retention, also because of the ecological value. But one has to consider that, especially when we are talking about wetlands and wetland vegetation did not learn really to use wisely the water, say, and especially in smaller rivers, and it might be that you have a loss because of the increase in evapotranspiration, and the precipitation does not immediately, produce precipitation at the same spot. So this has to be taken into account when you are talking about river basins, larger regions, and so on. In the end, it has to be really a large scale conversion of the landscape, so that really everybody, each region has a gain. Okay, and it has also to be a retention only in time. Here is the water balance of the Elbe River. This is most parts of East Germany belong to the Elbe River Basin, and precipitation, for example, is higher in summer, but river flow and water availability and runoff is lower in summer. And this is so because of the evapotranspiration. This is so because the uptake of, mostly the uptake of the vegetation. Yeah, and what measures we apply should in the end help to retain water in winter, spring, and release it over summer to harvest the water in the end. Yeah, there are, of course, many other actors, agriculture, roughly 50% in East Germany of the landscape. There are many different measures discussed: mulching, plowless tillage, enrichment with humus, agroforest, of course, in the end, one has to have a look at the effectiveness in the landscape itself. And what we try to do is that we implement all these measures in our landscape hydrological model and to see the effects based on measurements, of course, firstly, but then to upscale them and see the effects. Irrigation is, of course, problematic and possibly only for cash crops available in future in dry areas. And there are, of course, also some fancy ideas of alternative agri-photovoltaic. They have a lot of benefits, but I mean, they are in the end, of course, not the solution for everybody in really large landscapes. And sponge cities, of course, because you, again, harvest water, cool the area, and of course, also counteract floods, not only droughts, but also floods. Okay, the summary. What I think is from a scientific point of view, only the combination of many measures will be the solution. And to that end, all actors must work together, hand in hand, and cooperate. I think there should be a major transformation of the landscape. It does not help much when we do it in a spot here and in a spot there. Nevertheless, it will be simply not enough if we do not limit climate change. I mean, it counteracts, but it is not the only solution and not the solution in the end if we still emit greenhouse gases and do not mitigate. And with ongoing global warming, the extremes will, for a time being, continue to increase, and we have to adapt. Okay, with this, I would like to thank you.
Yeah, thank you very much. I found that really interesting, the change of the forest into broadleaf forest for production of more groundwater, because Ludwig Pertl, who was here yesterday, I don't know if he's here today, he talks a lot about the change needed in the forest to broadleaf forest to enable soil fertility, to increase soil fertility, for producing the soil carbon sponge, or more like a soil water sponge, as with the increasing temperatures, clearly the trees will evapotranspire more. So we need more water holding capacity in the soil, and this only comes with that change from conifers to broadleaf trees.
Yeah, it has many effects in the end. Obviously, yeah. Also the soil fertility health, the soil health in the end, and yeah, others.
Stefan, may I ask a question?
Yeah, very shortly.
What I found a little bit confusing is, on the one side, I understand you look at evapotranspiration as a loss of water, while at the same time it has a positive cooling impact, and you are more concerned about the discharge of the water or the saving of the water in the soil. But doesn't the evapotranspiration in the end, if the cycle works properly, lead to precipitation again? So I didn't quite catch that point.
Yeah, this is really something to be discussed in more detail, and looking at a spot. Yeah, the water which evapotranspirates does not fall down at the same spot again. So, and this recycling dimension, say, or scale is like 500 to some thousand kilometers. So there is, of course, a bit more dew and all that. But this is what I meant when I said you have to convert the entire landscape. So not the landscape only in East Germany or something. It has to happen also in France and in Belgium and what you have to gain more water here. So
okay.
This is and this, I think, is also scientifically. I mean, this is this scientific state of knowledge. And yeah, so it is in the end a loss, but it's also, again, of course, somewhere it drops down again.